We will now start investigating the moment of inertia of an area. Before we get into the calculations, I wanted to briefly go through an application of this property so you kind of understand why we're calculating this. And although we may not use it extensively in this course, in future courses you will use the moment of inertia of an area. Okay, so let's get to work here. So I have just shown a diagram here. You can think of this as a uniform beam, and we have force being applied directly in the middle of this beam, and on the supports here, since this is uniform and symmetric, the forces on the edges are F/2. And if you want to think of like a toothpick, right? If you hold the toothpick at both ends and then press down directly in the middle, where do you think this is going to break first? Right? Is it going to break somewhere over here, over here? I think most of you can realize if you apply a force directly in the middle of when you're holding a toothpick on both ends, I think you'll see that right here is where it's going to break, right in the center. So why does that happen? Why does it break in the center? Well, it comes down to our internal forces. And if we take a look at our internal forces of this beam, we see that the maximum moment along the length of the beam is right in the middle, right? It's FLO divided by 4. Okay, and that's where it's going to break. So it's important to know when things are going to break, all right? And we must compare these to some sort of criteria that is constant for all objects. And that is often what we call the stress. And this stress is denoted by the letter sigma, the Greek letter sigma. And this sigma here is really the measure of concentration of force. Okay, many of you maybe know stress is F divided by A. Now, for some cases that applies, but not for all cases. But really, it is a measure of the force divided by the area, right? It's some sort of concentration of force. Now, in this case, we don't have F over A, and this is an advanced topic here, but in this case, the stress is actually equal to my over I, all right? And sometimes we put a negative sign out here. But anyway, never mind that. This m is the moment, right? That's the maximum moment that we're looking for. And this I term is the moment of inertia of an area. So with that being said, if we want to lower the stress, if our job as engineers is to ensure something doesn't break, we want the moment of inertia to be as big as possible for the amount of material that we have, right? So, for example, we could make this uniform beam out of a solid circular rod, right? So the rod's cross-sectional area would look something like a circle. And that would be okay, all right? But really, if we want to save material, what we could do is make a cylindrical rod, but have it be hollow in the middle. All right. And if we did that, we would save on material, and this moment of inertia would still be quite big for this calculation. So our job as engineers is sometimes to make I as big as possible, therefore lowering the amount of stress in an object. So what objects or what areas have a large moment of inertia of an area? Well, we talk about things like I-beams. I-beams have a very high moment of inertia of an area for the material that it's using. And now we'll proceed to go into calculations on how to calculate the moment of inertia of an area.